This is a great trig question where we ultimately get to prove one of the addition formulas, this one down here in part 3. But first of all, we've got to focus on part 1, explain why CD can be written as A cos Y. Right, I'm going to highlight CD, here it is, and I'm going to focus on this right-hand triangle because it's right-angled, and I've got Y here. So I can write down that cos Y is equal to the adjacent, which is CD, divided by the hypotenuse, which is A. And the result then follows. CD is going to equal A cos Y. Next up, we've got the area of the triangle ADC. So this one on the left. I'm asked to show that the area can be written like this. All right. Well, so triangle ADC. And to be fair, maybe I should have written for the very first question, triangle BCD. Well, the area is going to be a half AB sine C. But that's for a general triangle where here's the angle C and we've got A and B. Um, so in this case, I can do a half times the two sides. So it's going to be B times CD multiplied by sine X. Now I can use this result from part 1. So CD is actually going to be A cos Y. Okay, and actually that's everything we need. It's going to be a half AB sine X cos Y. Now, part 3 says hence or otherwise show that this is true. Okay, so we've got to think about how on earth can we use the results from part 1 and 2 and this triangle to help us get the addition formula. Well, the sine x plus y's got to involve the area of the whole triangle, so it's ABC. Sorry, this is part 3. So the area is going to be a half times AB times by sine x plus y in brackets. And then remember we've got triangle ADC, that's the one on the left. That was a half AB sine x cos y from part 2. So when we compare, we can immediately see, right, I've kind of got this part, I've just got an extra half AB. I've got the sine x cos y part, I've just got an extra half AB. So now this is what I'm aiming for. And that's going to be the triangle on the right, so triangle BCD. Right, well here the area is going to be a half times A times CD times sine Y. Now the thing is, if I use the CD from before, then I've got A cos Y. That's not what I want. I'm going to get sine Y times cos Y. So we need to think of another, and this is the hardest bit of the question so far. We need to think about how else we could write CD. And instead of using A, we could actually use B. So we could write it as B times cos X. That's another way of approaching it. Because cos X is going to be CD over B. Wait, was it B? Yeah. And that means CD is B cos X. Okay, this is brilliant because I can now replace it. So it's going to be a half A times B cos X times sine Y. So that's going to be a half AB cos x sine y. And therefore, we can bring it all together. The big triangle must equal the two small triangles added together. There's a common factor of a half AB, so I can just cancel it out, and that's the result. Sorry, let me do that again, make it a bit neater. Really nice. Whenever I cover addition formulae, I always show where they come from, or try and get the students to work it out. There's lots of different proofs for them, and this is a really nice one. It's guided us along and got us to the addition formula for sine. It's great. So part 3, we've got an equation to solve, or at least not quite solve, but get the value of tan alpha. All right, I'm up for it. So the left-hand side, we can just use the addition formula as shown, and we can straight away write it as, like expand it basically. So it's going to be sine 30 cos alpha plus cos 30 sine alpha. And that's going to equal, and you can look up the addition formula for cos. I'm just going to write it down. It's actually cos A cos B plus sine A sine B. We haven't proven that one, but it's possible. You might want to look into proving that. It's quite interesting as well. So here I've got, this is going to be my A, and this is my B. Can ignore the minus because I'm using the formula now with the minus in. So that is going to be cos 45 times cos alpha plus sine 45 sine alpha. So it's time to either look up or use your calculator to get some of these exact values of trig, or you might know them. You don't have to know them for A level. I always think it's quite good to, but it's not. It's, to be fair, it's not a priority, especially if you're struggling on questions like this. Um, but it's an interesting topic. So sine 30 is a half, then cos 30 is root 3 over 2. There's lots of different ways to memorize these, by the way. And then cos 45 is 1 over root 2, or I'm just going to straight away write it as root 2 over 2. And the same for sine 45. Okay, I'm going to multiply through by 2 to get rid of all of these divided by 2s. That's good. And I want to get tan. To get tan, I've got sine and cos. I've got to try and get sine divided by cos. So let's get all the sines on one side and all the coses on one side. So next line is going to be root 3 sine alpha minus root 2 sine alpha equals root 2 cos alpha minus cos alpha. Factorize out the sine alpha. Just going to put it at the end. So root 3 minus root 2 sine alpha is root 2 minus 1 cos alpha. And just like you can cross multiply, you can cross divide, I suppose. I can divide through by cos and divide through by this root 3 minus 2. So sine alpha over cos alpha is going to be root 2 minus 1 all over root 3 minus root 2. We're nearly there. We can now rationalize the denominator. So I can times the top by root 3 plus root 2. You don't often get surds in the both parts, but it works in exactly the same way. We're using the idea of the difference of two squares to cancel this out. So tan alpha. Remember, I've got like double brackets now. So I'm going to get root 2 times root 3, root 6. Root 2 times root 2, 2. I'm going to minus root 3, and I'm going to minus root 2. All divided by 3. I'm going to get a plus, I'm going to add it in just because I want to show my work, and plus root 6 minus root 6, and then minus 2. So these cancel, and actually I'm just left to divide them by 1. So I'm going to get, as my final answer, I'm going to write it exactly like they've got, 2 plus root 6 minus root 3 minus root 2. Okay, big fan of this question, like the first part, but also this part here. Well done on your effort.